that works. Okay. Hello, everyone. Somebody say hello. Hopefully this is working. I have to get used to the.
Hi,
Okay.
it's working.
Hello.
Okay. So you can all read what's on the blackboard?
Yes, it's clear.
Okay. All right. So let's keep this very informal and feel free to interrupt anytime. And just as you did last week. So what I want to do today is say more about quantum spin glasses, and in particular, I'll start out by reviewing some rather old work with Jean Mouillet and Nick Reed that was actually done just before the SY work, which I will perhaps come to towards the end. So this is the model we want to look at. There's n sites. On each site, there's a spin, a quantum spin or a qubit, and any two sites are coupled with a coupling Jij, which is in the z direction. And then there's a transverse field, which points in the x direction. Okay, and we'd like to know the phase diagram of this model. And so it's a quantum model because this doesn't commute with this. Okay. All right, so a few quick things. When G is 0, of course, this is the SK model. The Sherrington-Kirkpatrick model is purely classical, and that's completely understood now. And it has a phase diagram that as you raise the temperature at G equals 0, there's a critical point, which was which is also all understood in this particular model as n goes to infinity, n being the number of sites. And so what we want to understand is what happens when you turn on G. Okay, so as I also mentioned last time, there's one very important simplification in this model, which is not shared by the SY model, which is that there's a limit in which there's a trivial ground state, quantum ground state. And that's the limit where G becomes very large. So when G becomes very large, the spins all just point in the x direction. So there's just a ground state which is unique. There's a gap, at least in the limit n goes to infinity. There's a finite gap. And as you decrease G, that unique trivial ground state is present. So what we would like to understand is what happens as you decrease the value of G and get more classical. And at some point, there's going to be a quantum phase transition, and presumably you're going to enter a quantum spin glass phase. And it turns out that at least in equilibrium properties, the structure of the classical spin glass phase here, and this whole quantum region is not very different, at least as far as the static equilibrium properties are concerned. So our focus will be really at very low temperatures and in the vicinity of this quantum critical point. Okay, so you can just start off by the usual canonical techniques and set up a path integral for a problem like this. Now, path integrals for Ising spins are a little bit tricky, although you can do it. You just have to discretize time. But if you want to work in continuous time, then it's a little easier to work with a slightly different model, sometimes called the quantum rotor model, where you just think of this realizing spin as a real field, which has two minima in some potential. So the model we'll actually work with will be, well, let me write down this Lagrangian. Lagrangian will be 1 over 2G, some real scalar field, d phi I d tau squared, and then the same coupling, Jij phi I by j. And then you want to put a potential, V of phi I, and V, will be something very simple with two minima. This is V of phi. So there are two states of phi, one here and one there, and those represent the two states of each eigenspin. And it's really, you can work with this or that. And the advantage of this is you can just work in a continuum time formalism and use all kinds of path integral tricks that are a little more cumbersome in this approach. Okay. So, right. So now we're going to take the larger limit where you can reduce everything formally to a single site problem where there will be no index I anymore, but there will be a replica index that you have to introduce. So you set up a path integral where you, as I discussed last time, the whole replica trick.
Don't you want the two states non-degenerate? The G times sigma.
Let's see.
Oh, no.
Well, yes, so, no.
G's like a hopping term.
Right, so in the limit G goes to 0, then the two states are exactly degenerate.
Okay.
Once you have a finite G, there's a tunneling, there's a symmetric and anti-symmetric state, and that's exactly the splitting between these two states. Okay, so the spectrum of this, the quantum spectrum of this has two states, and you want this splitting here, let's call it delta, that maps on here to 2G, which is the splitting here. So this, I should really call this G tilde, it's not exactly the same G. It'll have some complicated dependence on this G. Okay, but I'm going to drop the G tildes, and we'll refer to this model as easier to work with. Okay. So you set up the usual path integral where you take Z, the nth power, and then you average it. And so you end up getting a path integral over all the spins. And then you do the usual Hubbard-Sutanovich decoupling, which I'll just go ahead and do. And you end up with the following problem. Something, again, I'll be very schematic. It'll be there's a field QAB of tau and tau prime. And then you'll have product on I, integral d phi a of tau. And IA, sorry. So Q doesn't have any indices of space. And there'll be a term like, again, factors of 2 and so on. I'm not going to get right here. It'll be something like n j squared times integral d tau prime q ab of tau prime squared. And then you're going to have minus a term that couples these together, that d tau prime, sum on I, QAB of tau prime, phi IA of tau, phi IB of tau prime. And then there's, let me just call it L0 of phi IA, sum on I and A, where L0 is these two terms here, this one and this one. That gives you L0. So, L0 is just the quantum mechanics of a particle in some potential, which has, has some spectrum, discrete spectrum with no degeneracies, and we mostly will be interested in the lower two states. Okay. All right, so now the thing to notice is that the different sites I are totally decoupled from each other. So this path integral over d phi just becomes a product of identical path integrals. They all involve the same QAB. And so it's some path integral of a field to the power n. And so then you can easily take the larger limit. All the sites are gone. And in the larger limit, you also have, there's an n that comes out up front. So this whole thing here will give me, the path integral of this will define some z to the power n of, which is a functional of this function q.
Sorry, Doctor, could you just remind us what this is doing?
Sorry?
Before what you're about to say, the idea is that if you integrate over q, you get the original path integral for z again.
Yes, yeah. So if you do the integral over q,
Yes.
which is just a Gaussian integral,
Yes.
you get product of 4 phi's.
Yes.
And that's exactly the product you would get if you average over Jij over here. Okay.
Thank you.
Sure. So I skipped that step. You just average over Jij, you get product 5, 5, 5, 5. The most important point being here is that you get 2 phi's at one time and 2 phi's at a different time.
Yes.
There's no connection between them. And so the decoupling field has to be bilocal in time.
Okay.
So, and you end up with a theory that looks highly non-local, but of course it's not non-local because of the structure of the action you wrote down there earlier.
But you have to do the phi quantum mechanics seemingly with an arbitrary bilocal source q.
Yes, that's what you have to do. Correct. And that's in general not an easy problem for this, but for this particular problem, you can just expand in powers of q, and that gives you a reasonable answer, which can be checked by more careful computations and also these days numerical computations. So at least for this model, everything I think is not pretty well understood in this regime at low temperatures. Okay, so what I was saying with this thing is z to the n power of q, call it some other z. And so this thing is equal to basically dq, okay, leaving out the indices, exponential minus n integral of q squared, and then plus log of n log z of q. So in the large n limit, all you have to do is look at the saddle point equations for this. So what you have to do now, so now maybe Felix, you can flip over here. Does that work? Okay. So we're going to just take an action, which is an action functional of q, which will be, we'll have, okay, let me write it out completely now, d tau prime, mod QAB tau prime squared minus log of z, this z of q. Okay, and now in fact at the saddle point, we are interested in saddle points, and we're only going to look at the saddle point for now. Any saddle point solution will have a time translational symmetry. And so in fact, this QAB will be a function of tau minus tau prime. Okay. All right, and z of q is exactly just this integral right here. All right, so now from this object, so our central actor is this object, QAB of tau minus tau prime. And you can just see by undoing these transformation up to some constants, it's basically the spin correlation function phi IA of tau, phi IB of tau prime, with a sum on I and a factor of 1 over f. So this is the object that we're going to compute when we compute the value of QAB of tau minus tau prime that optimizes this free energy. Okay. So just from this structure, you can now see a few things. But first of all, you see right away why it has to be function of A tau minus tau prime, because that's it's this correlation function that only depends on the time. And from this, you can also now see that QAB contains the spin glass autoparameter, but in two different ways. And getting the two of them to match correctly turns out to be quite interesting and thing to sort out. So for example, I can look at what's called the replica diagonal correlation function, QAA of, I'll just write one time. And I'm going to, well, typically you sum over A and you put a factor of 1 over n if you want. Limit n goes to infinity. Sorry, not infinity, 0. This is little n. So this thing is just the autocorrelation function of a single spin in any given replica. And as time goes to infinity, that's what I wanted to take here. So as tau goes to infinity, this I'll call Q, or what do we call it, Q bar. And this is one measure of the spin glass autoparameter.
You took the diagonal matrix on the A equals B.
Yes, A equals A, yes. Okay. And this implicit limit, tau goes to infinity, means I'm really at 0 temperature. Things have become a little more complicated at finite temperature because there is no infinite time to go to. Time is periodic of length beta. Okay. So that's a very natural definite spin glass autoparameter because it just tells you dynamically, something very simple, that each spin is just freezing in the limit tau goes to infinity after you have set n to infinity. So you have a huge cluster and the spin is just frozen in a given state. It's never going to tunnel out of that state. At least the time it will take to tunnel out of the state grows very, very fast with the size of the system, probably exponentially fast. But we've already sent n to infinity. Okay, but another interesting autoparameter, which I also mentioned last time, is the off-diagonal autoparameter. N goes to 0 of QAB. And this is equal to, by the definition of the replica method, if you look into it, what this is equal to, this is equal to the following expectation value. Expectation value of phi I. This is just in a given set of Jij. And you square it and then average over Jij. So this is the equilibrium expectation value for a fixed Jij before I do any average over disorder. So just a thermal or quantum average. So that's some random number in any given fixed state, any given pure state, state where you don't tunnel into macroscopically distinct states. And you square it, because if you didn't square it, you just get a 0 average when you average over the disorder. But once you square it, and sum over sides if you want, but look at that. This is in fact the original definition of what's called the Edwards-Anderson autoparameter. They define it thermodynamically as this quantity.
Did you take tau to infinity here also?
Okay, so that brings me another point, yes. So now, actually, to be a little more careful, what I'm really doing, if I put a tau on top right here, phi I of tau, phi I of tau prime, average, you can see from the structure that, in fact, this is independent of tau and tau prime. The replica of diagonal components have to be independent of time. That's the only reasonable saddle point that's acceptable to us, because if you're in any equilibrium state, the average value of phi I is independent of time. So in fact, QAB in fact does not depend on this. It's independent of these. Okay. So that simplifies our task a little bit. You have to you can just assume right away at the saddle point level that QAB does not depend on tau or tau prime, or the off-diagonal components. Notice this is true only at the saddle point, is an expectation value. this path integral here is really a bilocal path integral for all the QAB. But after you take a saddle point and look at equilibrium states, saddle points, then the expectation value of QAB must obey this. But if you're looking at one of the other corrections, you will have to worry about the time dependence of the off-diagonal components. And that some of that was discussed in our paper, Green's Sextet in 95, 94, or something like that. Okay, but here I'll just focus on this. All right, so now our task is to minimize this functional. Before we do that, we have to evaluate this path integral. Okay, so this path integral in general, of course, is not very easy to evaluate, but a lot of work has been done. In fact, there's a nice recent paper by Peter Young where he's actually numerically evaluated this path integral for any ansatz of QAB, and then looked at these solutions. And all of its results actually agree completely with the very simple method I'm going to describe now. So the simple approximation we're going to make is just we're going to expand Z in powers of Q. And we claim we can do this in the limit where this gap is large. Of course, we don't want to make it infinite, but there is a gap. The local problem L0 has a gap. And this is, of course, the key difference from SYK. There is no such local problem in the SY case, but here there's a gap here from the tunneling between the two states. And so we can assume that, if I expand this out, all the correlation functions of phi, all the multiple correlation functions phi I'm going to get, decay exponentially with this gap. So any phi correlation will have some e to the minus delta tau decay. And we're going to treat delta as some kind of ultraviolet cutoff and really approximate this even by a delta function. Just assume it's very local.
So the tunneling gap, which is usually considered as exponentially small, here is treated as being big.
On a given site, on a fixed site, it's big. Eventually, there'll be a collective state whose gap will vanish, as we'll see. But that comes from the collective effects in the full theory from the QAB. But if this is a typical kind of thing you do for any Landau theory derivation where you or effective field theory derivation of phase transition, you introduce an autoparameter which is QAB, and then all other degrees of freedom are assumed to have only local correlations. Of course, in the end, any local degree of freedom does have long-range correlations, but that comes through the coupling through the autoparameter. Okay, so you have to feed that back in later. But for now, we can just go ahead and expand this out in power of Q. Okay, so that's very much the philosophy of Landau theory. So I'm going to take S of Q and just expand it out in power of Q. And this is, as I've already said, it's not something we understood how to do for the SY model. In fact, I tried it first for the SY model and gave up. So then we came to the simpler model where it all worked. And I think now we're starting to understand how to do it also for the SY model. But okay, so let's just talk about what we did. So now we expand this out. And the first thing you notice is that there's going to be a term linear in Q. And you do have to keep that. So, but let me not actually, there's a term linear in Q which I'll drop, and then I'll come back to it because it's a slightly more complicated structure. But you'll get terms like plus R integral d tau prime, sum on AB, QAB, tau. It's actually, yeah. Let me write it out in a more general notation that is needed to expose the full structure. QAB BA of tau prime tau. Then you'll get a term like plus U d tau QAA of tau QAA. And then turns out the another term, d tau prime, d tau 1, d tau 3, QAB tau 1, tau 2, QBC of tau 2, tau 3, QCA of tau 3, tau 1. And there's, many more. There's other cubic terms that actually Felix pointed out recently, which we didn't take into account, but they don't matter as much. Things like d tau 1, d tau 2, something like QAB of tau 1. No, actually, that won't be present for this model. But let me write on another one. I QAB of tau 1, tau 2 to the power 4. Okay, so this is the general Landau functional.
Why isn't there a term linear in QAA?
Yes, okay, that's what I was going to write down here. That's the empty space. But let me just describe the general structure of these terms and where they came from. So basically, you expand this out, and then you take correlation functions of phi in L0. Now, the first thing about these correlations, the two things about these correlation functions you should know. One is that they're replica diagonal, because there's no coupling between different replicas here. And second, they decay exponentially. So what that means is every time you have this thing, you can pretty much replace this by, in this expansion, by something that's replica diagonal and also delta function in time. Okay. So when you do that, then you can understand the structure of this. So this obviously comes from exactly just the quadratic order term here. Explain it to second order. Take the you get phi, 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 and you take expectation value like this. And when you do that and use that rule, you'll get this term. But there's another interesting term that you get, where you take the full connected correlation function, phi, 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 phi. This is also non-zero. And then they all four have the same replica indices. So that's kind of what happens here. And then all the taus become the same. So what the basic rule that you can see in all of these terms is the number of free replica indices is equal to the number of time intervals. Okay. It's true for every one of these terms. So finally, now I can tell you about, you have to put some dynamic somewhere. Right now, this is all time parameterization invariant in a sense, because there's no derivative with respect to time. And so that appears in the first term in this theory. There's some term, let's say, d tau prime. No, let me write it out over there. So there's a term over here that I'm going to write on the board over here, because that's quite an it out. So it's something like d tau. There's a coefficient which I'll call minus d squared d tau squared plus r of QAA of tau prime, tau equals tau prime. Okay. You have to first take the derivative and then set it to equal. So this is the only, the one term where we go a little bit beyond just replacing all correlation functions by a delta function. Of course, you can add derivatives to these terms over here too, but they don't make a difference in the low frequency limit. Or if you write it in frequency space, this is much easier. In frequency, so QAA only depends on tau minus tau prime, so there's only one frequency. So this just becomes something like d omega squared plus r times q. So, so there you can see the structure that omega squared plus r is very much like omega squared coming from d5 d tau squared times delta. If you think of Q as 2 phi's, that's simply just the bare kinetic energy of L0 with some gap R, the gap square root of R. I should make that just delta squared here, because I used R somewhere else. All right. Okay, so now I've reduced the problem to just minimizing this polynomial of a matrix. It's a 0 by 0 matrix, which is a function of time, where the diagonal component is a function of time. And so this is a problem that can be solved in essentially closed form, and many things can be worked out. Okay, so the usual Parisi spin glass theory is exactly of this form, except there is no diagonal components. The Parisi spin glass theory is only for the off-diagonal components. Yes, question? And these are time independent, whether you're in replica diagonal, whether you're in the quantum theory or the classical theory. So all the structure on the replica symmetry breaking and everything else is identical to the Parisi theory. Okay. All right, so if you want to learn more about the full solution of these polynomial equations, you have to read this paper by RS5. And it's not that hard once you have written down this action. Furthermore, you can also make some approximations. You can just assume it's replica symmetric. So you can take all the off-diagonal elements and make them make them equal to each other. And it turns out that the replica symmetry breaking is really not important exactly at 0 temperature in the limit that I've defined. It doesn't make very much of a role at all.
I'm having trouble seeing what kind of equation you get from that term linear NQ. Suppose you have an action that's QAB of tau prime squared.
Yeah.
That's this thing.
Yes.
So then what will this saddle point equation be?
Okay, well, I'll come to that.
Okay.
Right, okay. Right, so let's first work out here for large G, where the replica off-diagonal components are all 0. Then things are simple, and you can just ignore the replica indices and just figure out the kind of polynomial we're going to get here. So let's call, and we go to frequency space. So in fact, in frequency space, I'm going to call this D, D of omega, where Q of tau minus tau prime is equal to 1 over beta, sum of omega. Yeah. Okay. So then, functional in the replica. So this is the paramagnet. The function of D. Okay. So we get terms of various types. So this will give you basically sum 1 omega, omega squared plus delta squared, and D of omega. And then if you look at these terms here, let's just look at the quadratic terms. There are 2 types of quadratic terms, and they give you rather different structures. So this is QAB of tau minus tau prime, and this is tau prime minus tau, and you integrate over tau and tau prime. And so you get a term like something like this, some constant, A times sum 1 omega, D of omega, D squared of omega. That's okay. What did I call that term? R. Okay. And what about the U term? The U term will give you something different. It's an equal time correlation. So it's sum 1 omega, D of omega, whole square. And so on. So you'll get various higher order terms like that, where you'll get both terms that are take the square of d and then some over omega or something like this. Okay. In fact, yeah, and you can add a cubic term and so on. So, all right, so when you solve this equation, look at you solve ds by d of omega equal to 0, then what you find is, for example, this term just gives you a constant which is independent of omega once you take its derivative. You take derivative of one of them, the other one is independent of the external, this omega over here. So just a constant which you have to replace by a constant has no omega dependence, and then you have to determine that constant self-consistently in the end. And that leads to certain log corrections to scaling and so on, but I don't want to go into any of those. So let me just describe the basic structure that you get from here. You get a solution d of omega, which has it's a smooth function of omega. But you get a term which is, okay, minus or plus, I think it's minus square root of omega squared plus, let's call it g minus, well, okay. Let me call it m squared, where m is roughly some measure of the distance from the critical point. So there's a critical point, gc, and this distance is some function of m. And precisely what function of m it is it linear or has, in fact, it turns out to have some g minus gc times 1 over log g minus gc dependence. That's, that comes from this kind of frequency sum over here. So there's various details like that that I don't want to go into, but this is kind of what you get.
I don't see how it becomes non-harmonic. Your action is quadratic indeed. So
Yes.
the equation will be linear.
Oh, we have to include the cubic term.
Oh,
Yeah, without the cubic term, you don't have a phase transition. In fact, the simplest way to do this, which is what we did in the book, in the paper, you can actually get rid of the quadratic term. You can just shift q by a constant function of time, and you can always perform the shift so that the quadratic term doesn't exist. So in fact, this quadratic term doesn't exist. This one you can't get rid of. So in fact, the final theory, you only need 3 terms to get the full general structure. You need this term, you need this term, and you need the linear term. If you keep these 3 terms, then you can see the structure already.
the claim is that if you added more terms, you would just move the phase transition around, but not change its character.
Right. You won't change how this m depends on the distance from the critical point, and you won't change the square root singularity. And this has all been verified by numerical studies on models that don't even make this expansion. Okay, so then as n goes to 0, that's the question? We have a critical point. And at the critical point, at g equals gc, we have a prediction that d of omega is some constant minus mod omega. So that's a gapless spectrum. And so this tells us that phi of tau on the site, phi on any other site, doesn't have a gap, but decays is 1 over tau squared. That's the Fourier transform of mod omega. Okay, so that's this point here. You have 1 over tau squared decay. And that's a non-trivial prediction of this Landau theory. Actually, that was by Hughes and Miller earlier. And then we showed how the result was very general. All right, so the system, even though we started out with a bunch of gap states, we reached a critical point and the spectrum is gapless. Okay. So now, of course, the whole purpose of this presentation is to ask what happens when G becomes smaller than GC. How are you going to make sense of what happens there? Does this Landau theory give you a consistent set of results? And the answer to that briefly is yes. But it involves some rather subtle things that we have to work on. We have to look at both the replica diagonal and the replica off diagonal terms together and see what they give us. Okay, so first let's imagine that we indeed have a spin glass phase. And these are the two characteristics of the spin glass phase. One is that the diagonal correlation function has a Q bar. And the other is that the off diagonal correlation function is equal to the Edwards-Anderson autoparameter. Erase that. Okay, yeah. All right, so there are these two different measures of the autoparameter, and we actually want them to be equal if the system is going to make sense, because we want the thermodynamic equilibrium value to be precisely equal to the long-time correlation function. That's true at any time you have spontaneous symmetry breaking. It's always true that the magnetization is the square root of the long distance limit of the two-point correlation function. So, and it turns out that that does work, but it works out in a very interesting way, which involves the replica limit. Okay, so for now, let's just go ahead and see what happens if Q bar is non-zero, QE is non-zero. And just put it into these terms. Okay, so now there's going to be, we make an ansatz for Q. We're going to make a slightly different ansatz. So for the diagonal components, so now, what is this? So this is QAA is equal to this. And I'm going to assume that d of omega is a regular function. And, of course, we have to, let me call it the tilde, but I'll add a term here, which is bar. So there's a constant which is present at all times. It's a zero frequency component. So d of omega, which is the Fourier transform of QAA, is going to be d twiddle of omega plus beta times Q bar. This is just d tau, QAA of tau, e to the I omega tau. So this is the long time limit, which is non-zero, and d of omega is assumed to be a regular function, very much that is smooth function of omega as omega goes to zero. Not smooth, but it's not highly singular. This is exactly what you do when you're doing Bose-Einstein condensation. You put a macroscopic number of particles in zero momentum mode, and then some above the condensate part that's smooth. And here you're putting the macroscopic occupation of the zero frequency mode. So that's the Edwards-Anderson autoparameter. And then you also have the off-diagonal term, which I'm going to call QEA. Sorry, that's not quite the Edwards-Anderson autoparameter, it's Q bar. All right, so now let's look at the various terms. I'll go back here. Then S of Q. Okay, so what about the term linear? Well, the linear term is not terribly interesting because it not even sensitive to Q bar or QEA. It's only diagonal and tau is equal to tau prime. It's a short time thing. So it really doesn't change very much. It just remains what it is. It'll be exactly this with a d tilde. Okay, then what about this term here? So what you notice here is that there's something quite remarkable that happens. So this second term, so there'll be some regular term which I'm not interested in. I'm interested in the dependence on Q bar and QEA. So basically at long times, QAA is equal to Q bar. So when tau and tau prime become large, it's equal to Q bar. And so it's just a constant. And there's n of these things. And so what you're going to get is R times n times beta squared times Q bar squared. And then the off-diagonal terms will give you QEA, and that is n times n minus 1 and beta squared times QEA squared. Okay. And there's a similar complicated structure that appears from the W term that I won't write out. But I just want to highlight something very interesting that happens right here. So first of all, you notice that there's something highly dangerous. The action in any quantum system with a finite ground state energy must be proportional to beta, because the free energy is 1 over beta. The free energy that we're interested in of the physical system, so the average free energy, is it is the action times 1 over beta, and then per replica, which is n. So this is some free energy per site. You've already divided out by the number of sites, and that's per replica. And if you multiply it by temperature to get the free energy, because the action is free energy divided by temperature. And so this is equal to R, the one factor of n disappears, but you get a beta squared times Q bar squared plus n minus 1 QEA squared. Okay. Not beta squared, beta. All right, so as temperature goes to 0, this term is going to infinity. And that simply cannot be the case because the ground state energy per site has to be finite. There's some instability. However, what you now notice is that as n goes to 0, this becomes minus 1. So now you take the n goes to 0 limit, and then you put Q bar equals QEA, which is what we were hoping. Then you find the divergence disappears. And so what was potentially divergent seems to disappear, and this has to happen not in just this term, but term by term in the whole theory. And you also will get at 0 temperature exactly what you wanted, that Q bar must equal to QEA. Because if it's not equal, then you're, again, violating some fundamental tenets of statistical mechanics. Really, the fact that you're working in a pure state. Okay. Anyway, all right, so that's what you have to now check. And so now as a matter of algebra, you do play this kind of tricks to all terms. You don't have to actually impose this by hand. You just close your eyes. You take this ansatz and the ansatz for the off-diagonal terms. You can even break it up like a symmetry if you want. You put all of those terms into this expansion, and you just look at the Steiner-Bond equation and solve them. And when the dust settles, they're easy to solve and the n goes to 0 limit. You do indeed find this is the solution. And you include all these terms. And in fact, all the terms that have potentially divergent powers of beta disappear. In fact, the divergence becomes worse and worse. This term has a beta cube divergence. But that also will cancel out. I mean, it's easy to see why it must cancel out. Because imagine that Q bar equals QEA. Then this is just a constant matrix with whose every element is equal. So the number of terms is n squared. Or in this case, there are three indices. So this whole thing will be multiplied by an n cubed. and also beta cubed, when QEA equals Q bar. So the factor of n, will always accompany, extra factor of n will always accompany any potential divergences when these two are equal. Or another way to say it, if you put n equals 0, there'll always be factors of Q bar minus QEA associated with that. All right. So what is the solution you get at the end? So you get a solution where I erase my phase diagram. This is the spin glass. This is a paramagnet. And what we had found was that the phi-phi correlation function decays to 1 over tau squared at this point, at the critical point. And then here, what you find is that phi of tau, phi of 0, goes a long time as a constant, Q bar, plus, or actually, plus 1 over tau squared again. So that's the basic result. That in this entire phase, where you have, you have the full spin glass complexity, you have all these different ground states which are far apart from each other. If you counted the number of states, I believe that gives what's called the complexity, and that has a exponentially large number of such states. But in each given state, there's a 1 over tau squared decay. So an interesting question now is, this power, gapless behavior at this point, you could understand as some critical behavior. Even the Ising model has it without disorder. But an Ising model without disorder does not have gapless excitations in the ferromagnetic phase. But here it does. At least this model, we don't quite know what happens in the finite range model. This model does have it, and it's also been checked numerically as of some, by Peter Young in a recent paper. So I don't really have a deep understanding of where this 1 over tau squared comes from, what its proper interpretation is, but it's the robust behavior of a class of spin glass models, in which you're approaching the spin glass state from a trivial gap state. Okay, so that's all I wanted to say. What time is it? Okay, maybe I'll say a little bit about the more interesting model that we are currently thinking about and trying to apply these tricks for. But any questions from back at Harvard or elsewhere? Okay, you're all awake? All right, so let me just say a few more things about a different model then. So we'll take the following model. Again, 1 over square root of n. I less than j equals 1 through n. So very much like the model we've just considered. But we're going to take these to be Heisenberg spins, which don't commute with each other. And that's it. So you'll have an SU2 symmetry, although you can reduce that symmetry, I believe, and not get rid of the features we're going to see. So we can, go through exactly these are the same song and dance and reduce the path integral z to the n average to a path integral over dq ab tau prime exponential minus n q, well, The Q also has a bunch of replica spin indices. So really it's QAB, alpha, beta, gamma, delta, but I won't write them off. Okay, so it has many spin indices that I won't write out. QAB, tau, tau prime, because in the end, we're going to take a saddle point. And when we take a saddle point, the spin indices don't matter. Plus n log z of q. And what's the big difference now from the previous model is that z of q is actually much more complicated. So I'm going to assume actually QAB now is independent of indices, of the spin indices. That's because I'm only taking the saddle point as n goes to infinity. So z of q is this full integral. It's the integral of a unit vector of tau, which is also a replica index. And now there's a Berry phase term. I 0 to beta, A of S, the ds d tau. This just measures the I over 2. So A of S is the vector potential of Dirac monopole. S is on the unit sphere. So S is processing on the unit sphere. And then this is the term that tells you that there are two states which are exactly degenerate. And as long as that exact degeneracy on each side is protected by time reversal or some other symmetry, then this problem is going to be different from the problem that we looked at. And then there's a term just like the one we had before, which would be d tau prime, S A of tau, S dotted into S B of tau prime, times QAB of tau minus tau prime. Okay. So exactly the same structure as the model we looked at before, except the on-site problem is very different. If I remove the Q's, the zero L0, the analog of L0 has two degenerate states, which is, and you can't lift that degeneracy, or S degenerate states, any number. And so if you expand in powers of Q, you're doing degenerate perturbation theory, which just doesn't make any sense. So you can't just naively expand in Q. That's why this is so much harder. All right. So, okay. All right, so this particular problem, even today for SU2, this path integral hasn't been fully solved. We're making more progress in understanding it. There's been a numerical study by Henry and others of this model for SU2, and that's guiding us into which direction to look. But what we did in 93 was we said, well, let's just replace SU2 by SUM and see what happens. And that's where we got the SYK equations. So actually, you can, let me keep things exact. I mean, at this point, everything is exact, other than the absence of spin indices on Q. Let me just write down. So you can now, what you do is you take your spin, the spin operator, and you write it in spin notation, alpha, beta. So alpha, beta will go from 1 through m. So if you put m equals 2, then you have SU2. I'm going to call that F dagger alpha on every site and every replica, beta. And now I have a constraint, sum on alpha on every site and every replica, F dagger alpha. F alpha is m over 2. So for the simplest case, m equals 2, I have two types of fermions. And only one of them can be allowed because the total number of fermions on each side has to be 1. And so this is the usual spin a half representation of a spin with Pauli matrices and so on. Okay, so what you do now is you take this representation and plug it in there, and the whole Berry phase terms can simplifies into the usual canonical fermion path integral with the Lagrange multiplier to implement this. And then Z of Q can be written in the following form after a few tricks. So you can write Z of Q in the following form. And I'll write it in a form that will make the connection to SYK very obvious. It's a G sigma path integral, GAB of tau tau prime, D sigma AB of tau tau prime, exponential. Yeah, I'm going to have to look this up now. This is relatively new work. Okay. So it turns out to be minus M. There's an M out front where M is this index, which is 2 for the case we really care about, minus log get delta of tau prime, delta AB, I lambda, okay. All the indices there. Lambda is another, there's another pattern here, V lambda A of tau. That's the Lagrange multiplier that imposes constraint. That's not so important. And then let me go over here. Plus d tau prime, then you get sigma AB. GPA tau prime. And at this point, you should, this term and this term are based exactly the things you get in G sigma path integral for the SYK model. The only new thing, or this is actually the older thing, J squared over 2 QAB of tau prime times GAB of tau prime times GBA of tau prime. And that's it. So this thing in the SYK model is G to the power 4. But now if you notice, if I take the large M limit, because there's M out front, it's M multiplying everything. If you take the large M limit and take the cycle quantity equation for Q, oh, sorry, this should be Q squared. So you'll just get Q equals GG. And therefore, this just becomes G to the 4th. And then you're back to the SY brackets K equation. The equation already in our paper. Okay. So that was the long route to how we came up with those equations. That's kind of gone through here. So now we know, of course, for the SYK model, there is no spin glass order at M in the SYK equations. And what that means is that any spin glass order that's going to appear must involve corrections at order 1 over M. You can't go get M equals infinity if you want to see the spin glass state. Now there's numerical evidence that there is spin glass order in the SU2 model for M equals 2. And so what we've been working on recently is to try to understand that by understanding something about the structure of the 1 over M correlations. So that's pretty much work in progress. Let me just give you a little taste of the result we think we're pretty confident of at this point. Let me actually say it, it's really easier to say in frequency space. So if I look at the the spectral density if I define the correlator chi of tau, in this case it would be S of tau dotted into S of 0. Okay. So in the SYK solution, this goes as 1 over tau because it's the product of two G's, and G goes as 1 over square root of tau. Let me say, so chi of tau, chi SYK is GG, 1 over tau. Okay. And then chi spin glass, we know this goes to constant Q bar as tau goes to infinity. And so we would expect that if the spin glass order was small, there was some frequency range where this was true. So let me also write this in frequency space. So if I look at the chi double prime of omega, SYK, at small frequencies, that goes as sine of omega. And what we learned, chi spin glass, in the Ising problem, that went as Q bar plus 1 over tau squared. And in the frequency space, this is chi double prime of Ising, ignoring the delta function at 0 frequency, at finite frequency, that's not sine omega, that's just omega. So this is the usual, dissipated term when you have ohmic resistance, chi double prime omega going omega. So what do we get? So what we know, we're pretty confident what happens by solving this equation and looking at it more carefully with 1 over n directions. Is that, so chi double prime of omega, let's say for SU2, this is our guess. So since the spin glass order is small, so let's imagine Q bar is small, which is what numerically seems to be the case. So there's only one scale, which is the exchange constant J. And we know what, at high enough omega, we're hoping that you see SYK behavior. And in fact, that's what you see. It goes to a constant, and in fact has a linear omega dependence. So in fact, in SYK, we also know the first correction of this. So it's sine omega minus constant times mod omega. 1 minus constant times mod omega. And this mod omega is the graviton, the boundary graviton that comes from the short chain. This is the first correction from the short chain. And numerically, we seem to be seeing that as a linear, it's actually more linear than I drew it. Looks like this. Okay, so this is graviton, question mark. Anyway, that's what Henry and I proposed in our previous paper. But then what happens at very low frequencies? Well, you're going to get the delta function, which I'll just put schematically over here. So what we're able to show is that, in fact, as you approach very, very long times, you go back to this decay. So this SYK behavior gets quenched, and it goes linearly in omega. And this peak is at a frequency omega, which is J times Q bar squared. So that's really great because, Q bar is measured to be around 0.02 numerically. So this is very small. So up to a very small frequency, when the spin glass order takes over, it seems like you get pretty much the SYK physics in this model for SU2. And also this going to 0, like this, implies that the entropy disappears. When you try to compute the entropy, there is no 0 temperature entropy associated with these quantum fluctuations. It's all presumably now hidden in the entropy of the various spin glass states. Okay. So that's to come in a paper with Main and Felix, hopefully in a few weeks. Assuming it could be wrong, but up to here, everything's fine. All right. Oh, where did I close this? You can all hear me, right? You're still alive. Yeah.
Yes.
All right, that's, I don't have anything more to say.
So question?
Yeah, go ahead. Yeah, Darshan?
Yeah. So in this analysis, so in large M limit, you have the SY solution, and SU2, there is a spin glass. So if
Yeah.
you do this systematic 1/m kind of corrections, do you get like some critical value of M where there is a phase transition then from the spin glass to?
That's a great question. That's a very good question. In fact, you don't. And this was something in the paper about which I have to turn the sound off on it.
Yeah, sorry, I can't hear you properly.
Yeah. Okay, you can hear me now?
Yeah.
But I should, yeah. Oh,
Yeah,
I
that's
should turn.
good. Yeah, that's good.
You can see me, okay. Now you can see the board, okay. Yes, that's a good question. So if you carry out this expansion, so what you can do without too much trouble is do this expansion. You know, I said you can't do the expansion in powers of Q, but let's just take the off-diagonal components of Q and try to expand it, because the spin glass order parameter is 0 at m equals infinity. So if you look at the S of Q, and now I'm going to take QAB for A not equal to B of tau prime. I'm just going to call it little QAB, which is what it is in the classical theory, because it's independent of tau and tau. So there's a term that looks like this, which is QAB squared. In fact, comes with a beta squared. And that has the term is something like 1 minus j times chi of 0 frequency, or whatever temperature you might happen to be at, whole squared over 4. So this is, very much like when you're doing ferromagnetic order, and you're doing the about coupling, the quadratic term has this RPA form, 1 minus j chi. In this case, this chi squared, this quantity here, is called the spin glass susceptibility, chi spin glass. This is what it is, by the exact definition of spin glass susceptibility. The spin glass susceptibility, or inverse of it, sorry. It's proportional to the inverse of the spin glass susceptibility. Okay, so when this hits 0, you have a transition. Now there's also a factor of m here. Okay, so at m equals infinity, there's no problem, it's positive, and m has gone to infinity, so this term is 0. But what is chi omega equals 0 of SYK in the m equals infinity theory? Well, I told you the decay is 1 over tau. So when you take a Fourier transform, that goes as log of j over t. So this tells you that there is a critical temperature to spin glass order. Tc is j times exponential minus some constant times the root of m. So it seems that for any finite m, there's an exponentially small temperature for this model anyway, where there is spin glass order. This was in the paper of George Farquhar and myself in 2000. This was out. Right, and so now, from now we know numerically, this number is still pretty small, even for SU2. At least the spin glass order parameter is very weak. So the solution, SYK solution, seems to be quite reasonably well behaved because these effects are quite small. But we couldn't have known that without some actual numerics. And these are all reasons why people didn't take the SY solution very seriously for a long time.
I see. Thanks.
Sure. Okay, good. So have a great weekend. And if you have volunteers for the talk next week, let me know.
Thank you, Mr. Bear.
Okay. Turn this off. So I think, let me just end the meeting.